Welcome back to all the students and good morning to all the students. And yesterday we have discussed the histogram process. Histogram process, and in the histogram process there are different procedures are there. Um, Histogram equalization, and the next one is histogram matching, local histogram, and histogram with statistics. These are the main four types. Out of this, we have completed the histogram equalization in previous class. So today's class we have to start our class with the histogram. Histogram matching. Right. Just wait. The main topic is intensity transformations and spatial filtering. In that, some transformation functions and histogram process is over. Okay. Today, histogram equalization is over. So, for this we have completed. Am I audible? Anyone respond, please? Hello? Hello?
Yes, sir.
Okay. Histogram matching. As like our histogram equalization, next one is histogram matching. So, however, what is the application of histogram equalization? In histogram equalization, we are enhancing the image. Actually, in that histogram, we are equalizing the histogram of the pixel values of that particular image by using some transformation function. But in the case of histogram matching, it is unlike our histogram equalization, but here the difference is already there is some histogram of a original image. Let us consider PR of R. But this PR of R, just wait.
Sir, doctor.
But this PR of R, ఎవరమ్మా మ్యూట్లో ఉన్నా కదా? But this PR of R is our input pixel, input image histogram. Let us consider. But this input pixel or input image histogram can be specified or can be transferred or can be matched with our a new histogram. That means we are completely changed nothing but modified or matched our input signal, input image histogram to the another specified. That means we are specifying. So due to this reason, our histogram matching is also called as histogram specification. Nothing but we are specifying the our required histogram to the our particular image histogram. So here I am considering there are two types of histograms. PR of R is my input image histogram. Let us consider I want to modify it or I want to match this histogram to the PZ of Z. So these two denote the, of course, continuous probability density functions. So that means let us consider already we know histogram nothing but a random variable. So R is input random variable, Z is after transforming the histogram into the another histogram process. In that Z is another random variable. Of course, R is a random variable scale and Z is also random variable scale. Let us consider PR of R is our input image random scale and Z is after transforming or nothing but output image intensity transform intensity scaling random variable. So R and Z. So we have how many two variables? We have the two random variables R and Z. R and Z. Just wait. And here's so this R and Z, there are two random variables. So now let us consider Pz of Z is the specified probability density functions. So now we have let us derive the transformation function. Let us consider. Let S be the random variable with the probability S equals to TR of R. As like our in our linear histogram equalization, here also a simple transformation function. First of all. So let us consider S equals to T of R, nothing but L minus 1, same as there is no change in this transformation function. But we have another new variable that is called as Z. We have to define that random variable with probability density function like this. So how many variables here? R and Z. So this is a transformation function for R. Similarly, another transformation function for the new specified, that means our required histogram, here I am taking G of Z. Let us consider just G of Z. Remember this transformation function for input image. But what is our requirement? I want to match this transformation function to the specified histogram. Okay, I will explain the example problem clearly. Don't worry. Okay, so define a random variable Z, and that is also with the probability density function G of Z equals to L minus 1 integral 0 to Z Pz of T into dt. So both expressions look like same, but variables are different. And now this transformation function is matched to this S. But what is S? S is my transformation function with the which is obtained by using the input histogram or PR of W. That means this transformation function is actually derived or obtained with the help of my input image histogram. But what is G of Z actually? This is also another PDF, but which is obtained by our specified histogram. By our specified histogram, and which must be equates to or match to this our derived transformation function of our input. Have you got the point? Remember, there is one image, and that image is having my PDF or histogram like this, here of R. Okay. But I have some set of histogram points or probabilities, and I am specifying with the PDF PZ of Z. So, how many PDFs? Input PDF, let us consider, and after matching the PDF, PZ of Z. Okay. But as per our normal mathematical procedures, we have to derive the two transformation functions. So what are the two transformation functions? For first, as per the normal procedure, S equals to T of R equals to L minus 1. This is for only with the input image histogram. But another PDF is also there, which is derived by our specified histogram, that is Pz of Z. By using the Pz of Z, also we can derive the transformation function, which is named as capital G of Z. Here T of R, but here G of Z. And that must be equates to yes. Then only our histogram process is completed. So this is the process, and now here mathematical relations are there. How we are going to, that means this is S equals to T of R is obtained by normal procedure, but G of Z with a specified histogram, and which is must be equals to S. From this, what we can say this, so S equals to G inverse of, or Z equals to G inverse of S. That means S is inverse to Z, Z is inverse to S. So this S is replaced with your T of. Have you got the point? I have two PDFs. This is PDF for input histogram. This is also PDF for specified histogram PDF. But it is equals to S. So from this we can derive definitely Z is capital G inverse of S. Nothing but our our input image transformation function is definitely inverse of your specified Z. So this is I am showing mathematically G inverse of T of R. Simply your S equals to T of R, and if your T of R is replaced with this PDF, we can calculate Z. This is another process. Okay. So now there is a procedure for histogram matching. So what is the procedure for histogram matching? First, obtain PRR, PRR from the input image, and then obtain the values of S. So what is the first PRR? There is a, let us consider one image. From that image, we have to obtain the histogram values. That means probability values. Okay, if you know the PRR value, definitely we can obtain the S. What is S? It is a transformation function. It is a PDF, probability density function or transformation function we can calculate. So after calculating the PDF of your input image, what is the next process? Use the specified PDF. This is our we are proposing. Actually, what is specified? We are proposing our PDF values, our random values. That is our designer values. Okay, na? Okay. By using our specified PDF values, again we have to obtain the transformation function G of Z. Like our T of R, S equals to T of R, we have to derive the G of Z. So what is G of Z? G of Z is also a PDF, but which is obtained from the specified PDF values, from the specified histogram values. Okay, we will get it. But it is equals to, and after you got your G of Z, just it is equals to your S. Okay. After equating S, just simply mapping from S to Z. So nothing but what is the value of S in our input PDF is just simply equals to your Z. So for suppose S0, Z0, S1, Z1, S2, Z2, S3, Z3, and so on like that. It depends upon your number of scaling values we have obtained. For suppose if you take 8 scale, 8 scale means 0 to 7. So that means S0 input side S0 to S7, output side Z0 to Z7. Like this we are getting, or we are mapping the values, and then we can, with that we can complete our histogram process. Once again I am repeating here. First of all, there is one image, and in that image first obtain the values, that is probability values P of R from the input image, and then calculate the transformation function T of R, nothing but S equals to L minus 1 into integral 0 to R P of R W into dw. Just simple transformation function using the input image. And second step is just simply again calculate the transformation function, but in this case the probability values are different. That means our proposing intensity values are that means probability values. Then with that we will get some different transformation function, and which is equals to the our derived input signal, yes, that thing. But simply here there is a mapping. In that mapping, your Z is mapped with, or S is mapped with your Z values. Okay. Next. So here, first, as like in our equalization process, first we have to consider continuous. What is this signal? What is this PDF? Continuous. So PR, let us consider my image is having PR of R equals to 2R by L minus 1 whole square, and for 0 less than equals to R less than equals to L minus 1 and 0 otherwise. This is my function, PDF function. So and also I'm specifying. What is my specifying? That means find the transformation function that will produce an image whose intensity PDF is like this. So ఎలా ఉండాలి, ఇది యూజ్ చేసుకొని ఒకటి S derive చేయాలి, but that S is must be produce this transformation function, or this transformation function which is must be matched with the PDF. So here I am proposing my specified PDF of specified histogram or histogram matching is like this. ఇలా ఉండాలి అంటే ఈ ఫంక్షన్ యూజ్ చేసుకొని నాకు ఫైండ్ అవుట్ చేయాలి. జస్ట్ సింప్లీ ఫాలో ద ప్రొసీజర్. So here what is S? What is our requirement? We have to derive the S which is equals to PR of R, which must be equals to PZ of Z. That means Z. So how it is look like? So T of R equals to just L minus 1 into this is normal formula. L minus 1 is same, integral 0 to R. Your input function PR of R omega is modified with the dummy variable 2W. So actually in that our function there is a 2R. So here replaced with the dummy variable 2W by L minus 1 whole square to dW equals to, and if you calculate the integration, you will get R square divided by L minus 1. This is our uh, transformation function for this input image PDF, but it is must be equals to what? So to equate again what we have derived g of z using this pz of using this specified pz of z, again calculate g of z. So this is my g of z. So what is g of z? In g of z, L minus 1 is same, integral 0 to z, but pz of t, here I am using another dummy variable t, so actually pz of z, just replace this pz of z, and that is 3t square by L minus 1 whole cube into dt. So again we have to integrate this, you will get z cube by L minus 1 whole square. But this is equals to what? S. But what is S? S is nothing but your R square by L minus 1 or just S. So simply from this transformation function I am deriving Z value. So just equate Z equals to S equals to Z cube by L minus 1 whole square. But I want Z. That means this cube value will be one third of square, one third of L minus 1 whole square into S. But what is S? Your S value is replaced with R square by L minus 1, and you will get L minus 1 into R square whole power 1 by 2. So this is my transformation function to obtain my specified histogram values. Okay, and remember this is continuous image or analog image. Continuous image or analog image. So, but in our digital image processing, we are using not analog signals or not analog image. So instead of that, we are using what is that? Discrete values or digital values. So simply I am changing my integration symbol with summation just. So what is again procedure? Same procedure. There are 3 steps. So out of the 3 steps, what is the first step? Here PR of RJ. So here there is another integer value is there. What is that integer value? What is that integer value? J. What is the reason? I am using discrete, not a digital. So simply S suffix k is also digital, is discrete, and T of R suffix k equals to L minus 1, sigma j equals to 0 to k, PR of Rj simply, but here another element is there 1 by Mn. What is the reason? How many pixel values? Over Mn to N image, there are number of pixels are L minus 1 divided by Mn into sigma j equal to 0 to k n suffix j. This is my input signal or input image transformation function with the help of input image histogram. Okay, same again. If you specified G, that is Pz of Z. So how we are getting G of Z cube? That means G of Z is my PDF, but with the use of Pz of Z. With the use of Pz of Z. So G of Z Q equals to L minus 1, same, Z I equals to 0 to Q, Bz of Zi, but this transformation function is equals to your Sk, the suffix k. So now if you equate these two, and if you want to get your Z, how can you get? That means nothing but mapping. And Sk into Zq. So Z to Q, Sk. Already I told you, Z0 equals to S0, Z1 equals to S1, Z2 equals to S2. Like this we are mapping. Simply the same as like your analog. But in previous case, continuous PDF, but this is discrete PDF. Simply discrete images or sampling values. We are using the sampling values. Okay. So here now I want to explain the same histogram matching with an example. So already we have take one example, that is, did you remember? This is my table, previous table, but this table is used for histogram equalization. Okay, na? But the problem is different, the process is different. What is that? Along with this, we need another table. What is that? Already I told you, specified. We are specifying this. So what is my specified values after transforming input side? We are calling as R0, R1, R2, R3, R4, R5, R6, R7. These are my input image scales range. But I am changing, I want to change the same scale values with this specified properties. Actually, my input image having the intensity scales with the probabilities like this. With this property, what is 0.19 is having 790 pixel values. 0.25 having 1023 pixel values. Okay, these are my input image pixel values, but which are matched to your specified values. Like this, I want to transfer. Okay, so using these two tables, what we have to do? What are the three steps? The first step is, what is this? In this, obtain the PR of R, and after that, already we have the PR of RK. From this, we can calculate S. What is S? S equals to TR of R. TRK, T of RK. So there is a formula, and how many values we will get? Again, R0 to R7. So S0 to S7. We will get S0 to S7 values. So those S0 to S7 values are mapped to Z0 to Z7. Simple process, right? So first, what is the process? Obtain the S. How we are getting S? S is nothing but your equalization. Remember, all of you, S is nothing but your equalization process. So in our equalization process, instead of R0, we are getting S0. Instead of R1, we are getting S2, S1. Instead of R2, we are getting S2. Like this, we are getting S0, S1 to S7 values. After you are getting S0 to S7 values, just simply maps to your Z0 to Z7. That is the simple process. So here I am considering my 3-bit image. In 3-bit image, how many are L? 8. 2 power 3. 2 power 3. 8 equals to 2 power 3 minus 3-bit image. So size, what is my size? A 64 into 64. How many pixel values? Same pixel values, 4096. So for this image or MN pixel values, and the probabilities will be like this. And for this histogram, I want to specify the histogram like this. This is our requirement. If you want to change, just you can change it, whatever. As per your random requirements, we can change this value. This is not a fixed. Okay, na? According to that, your histogram matching will be changed. So that is the process. Okay, how it can be proceed, we can see the graphical notation. First of all, after calculations. So what is my calculation? What is my first S? So this is S. These are all S. What is the formula for S? What is the formula for S? S equals to TR of R equals to, what is it? 1 by Mn sigma j equal to 0 to k. What is it? PR of RK into the pixel value. That means if you multiply the values, the previous one value. How can you S0? What is the formula in the equalization process? Just wait. This is S0. How we are getting S0? TR of R0 equals to 7 into sigma j equal to 0 to PR of R j equals to, that means 7 into 0.19 like this 1. The same values. Don't confuse. These are the same values. So just I am again showing here. That means don't bother about analog. We are in digital, right? So what are the values? 1, 3, 5, 6, 7, 7. These are the values. So with this, our first step is over. What is the next step? Next step is also another value is there. Compute the G0, G1, G2. But these G0, G1, what is the formula? As like same formula. But here the probability functions, probability values are changed. So what is this first function? 0.00. Okay. What is this first value? Probability. Pz of zq. P0, z0. How much? 0, 0. So if you place this what happened? You will get 0. In the second one, pz of z2 also same. But in pz3, how many values? 7 into how many values? Add 3 values. 0.00 plus 0.00 plus 0.00, right? So you will get Z2, Z1, Z2, and Z3, Z4, Z5, Z6, Z7. So here are so many transfer functions. So these are the transfer functions. These are also transfer functions. But these transfer functions are obtained. Transfer function values or transfer function discrete values will obtained from the input image histogram values. But what are these transformation functions or transfer functions values? These are obtained from specified values. That is a difference. Okay. 2 steps are over. What is next step? What is next step? Here I am graphically showing that. First of all, after this, just draw the 2 histograms. So what is this first figure? A histogram of a original image. This graph is drawn using the values. What are the values? These are the values. Okay. After this, B. What is B? B is a specified histogram. Render. Second one. What is second one? These are the values. Okay, na? So using two tables, we have drawn 2 histogram values. So this is our original image histogram, and this is our specified histogram. Okay. After this, what is our G of ZQ? G of ZQ is simply these are the G of ZQs. Using these values, we have drawn a transfer function. That means using these histogram, specified histogram values, we have drawn the transfer function of G of ZQ and drawn like this. Okay. But after mapping, this fourth figure I will show later. For these values G Z of Q, how we are mapping here, I am showing you. What is S0? What is S0? S0 equals to 1. So which is mapped to what? Z3. What is the reason? S0 equals to 1, and in our specified it is equals to what? G of Z3. That means it is equivalent to Z3, not Z1 or not Z0. Remember that. The same S0 may not be equals to Z0. We have to equate the values. Since here my S0 equals to 1 and it is mapped to what? Z0, Z3. Okay. Similarly, what is S1? S1 is value is 3. So here where is S1? So this is my S1. Okay. Next. So here I am showing the S0 equals to 1, S1 equals to 3, S3 equals to 5, S3 equals to 6, S4 equals to 7. Like this we are having. So simply S suffix k equals to 1 to 3, 3 to 4, 5 to 6, 5 to 5, 6 to 6, 7 to 7. So how many values? 2, S0, S1, S2, S3, S4, S5, S6, S7. Here S4, S5, S6, S7 all are equals to Z7, but S0 equals to Z3, S1 equals to 3. S1 equals to 3 means, so in this obtained value there is no 3. So what is rounded to? Don't confuse. Here there is a 2, but nearer value. So here actually S1 value is 3, but it is equals to 2. What is the reason? There is no nearest value. So that is the reason it is equals to Z4. So S0 equals to Z3, S1 equals to Z4, S2 equals to Z5, S3 equals to Z6, and remaining all S4, S5, S6, S7. 4 scale values are just simply equals to S7, G7. So These are all I am showing one table. Okay, 1 to 3, 3 to 4, 5 to 6, 5, 6 to 6, 7 to 7. So on approximating this value, my SK value 1 to 3, 3 to 4, 5 to 5, 6 to 6. So using this value, here I am showing first RK value, R0 to RK value 0 to 1, 1 to 1 is mapped to 3. Similarly, 1 to 3, but 3 is mapped to approximate value 4, and 2, 2 is 5, 5 2 is directly 5, and 3, 3 2 is mapped to, that means obtained your transformation function value is 6. 6 is directly transferred to 6, but remaining 4, 4, 5, 6, 7. These 4 scale values are having same transformation after transferred 7, and the same is mapped to your 7th scale. So how many scale values are mapped? So after specifying, after your histogram specification or our histogram matching, how many scaling values? Actually, our input side, how many scaling values? 7 are mapped to 1, 2, 3, 4, 5. What is the reason? The last 4 scale values are having same scale value after histogram equalization and specification. Just simply, this is my input side, and this is equalization, and this is specification. Input histogram, equalization histogram, and what is this? Matching. Right? So here I am showing again. Simply all values. I am skipping middle one, equalization. We are concentrating on matching. How we are matching? R0 equals to first scale equals to 3, R1 equals to 4, R2 equals to 5, R3 equals to 6, R4 equals to 7, R5 7, R6 7, R7 7. That means input side, these are my scaling values, but output side definitely match it to another scaling values. So what happens as a simple observation, definitely due to the scaling values are matched to another scaling values, what happen? Enhancement. Enhancement means your intensity values will be changed from one scaling values to the another scaling values. So I will show again graphs. Here I am redrawn our histogram are equalized. So this is original, this is specified. These two are our input side. Original, specified, after transformation. Using these specified values, this is my transfer function with the specified values. So the last one is, what is the last one? Resultant of specification. That means these values. What is my R0 value? 3. What is my R1 value? 4. What is my R2 value? 5. What is my R3 value? 6. What is my R4 value? 7. These are all 7. So this is 7. Okay. So based on this, what is, instead of R0, what we have to consider? R3. So Z3. Instead of R1, what we consider? Z4. What is, instead of R2, what we have consider? Z5. Instead of R3, what we have consider? Z6. Instead of R4, Z7. Instead of R5, Z7. Instead of R6, Z7. Instead of R7, Z7. So however, how many scaling values? 1, 2, 3, 4, 5. 5 different scaling values are known. So my horizontal pixel scaling values how many? 3, 4, 5, 6, 7. Okay. For 3, what is my probability? Here. Z3. What is my probability? For Z3 probability 0.15. Here 0.15. Similarly, Z4. See the probability in specified, and Z5, Z6, Z7. So after we got mapping, simply use the specified properties. Simply use the specified. Now compare B and D. What is B? This is B. What is D? This is, so this is input side specified. This is input side specified. Remember, this is my original image histogram, but this is my input side specified. This is I am specifying. So if you give these to your digital image processing system, what happens? Which find out the transfer function, and after this finally mapping. After mapping, specify the histogram values. That is the process. So simply here I am showing R0, R1, R2, R3, R4, R5, R6, R7 are mapped to your histogram specified scaling levels. But these scaling levels are having different properties. What are those properties? Those properties I am showing in our table initially. This is my table. Okay, now out of this table, I am using not all scaling values. What are the scaling values? 3, 4, 5, 6, 7. So these 5 values are only showing and final mapping. So and my graphs will be like this. So these 4 graphs are showing your histogram matching. It's very easy. Don't confuse. This is my original image histogram. This is also histogram, but which is specified. And this is the transformation function with the help of specified this graph, this graph transformation function. Okay, after transformation function we have derived, we use the mapping process. This is mapping or matching. After matching, redraw your histogram. But in this histogram, we are considering only, in our example, only we have how many scaling values? 1, 2, 3, 4, 5. That means 3, 4, 5, 6, 7. These scaling values only we have considered. Actually, input signal, how many scaling values? 7 scaling values. But output after histogram matching, how many scaling values? Only we have 5. What is the reason? In our histogram matching process, the last four, what are those? Last 4, 5, 4, 5, 6, 7. These are having same equalization value. So due to this reason, it is shifted to single and replace only single scaling value. Here I am showing. Okay. So like this, we are having histogram process or histogram matching 0.15. That means the last scale value is how much? The last scale histogram value 0.15. That means like this. Here I am located. So if you compare B and D, definitely this is specified histogram, but this is also histogram after matching, after specification completed. Your process completed. So now we have to check how the histogram matching is applicable. So here I am showing again what is this image of the Mars moon photo probe probes taken by the NASA. But here what is my histogram? Since it is a dark image, what is my histogram? Left side, and some part is contrast is high or light image. So there are 2 histograms. This is a combination of 2 histograms. So this is, have you observed? 1 minute. This is the part white and this is the part black. So this is a combination of 2 histograms. So here this is histogram for dark, and here this is the part histogram of a white. That means what is the reason for small part for the white. So here, in our original image also there is a small amount. Small part is white, remaining part is black. Hello, am I audible or not? Anyone respond? Hello, hello.
Audible, sir.
Okay, thank you. So this is my original image. I want to perform the histogram matching for this image. Okay, for that, here I'm using my transformation function like this. My specified. So what is my specified function? This is my specified function. Okay. So in this specified function, I'm using how many scale values? 0 to 255 on our input side, output side also 0 to 255. Okay. What is second figure? A, B. What is B? Histogram of equalized image. After equalization, what happens? Compare previous one, this one. So this is original image. After equalization, your dark pixels also having some changed. So what is this area? What is this area? Changed or not? Somewhat. That means due to this histogram equalization. So what is in our? There are 3 steps in our histogram matching. First, take the original image. After that, perform the histogram equalization. After that, histogram matching. Histogram equalization, histogram matching. That is the process. So in second step, what happened? Histogram equalization. Due to histogram equalization, my after histogram equalization, my histogram is changed like this. Histogram is changed like this. But actually, what is our original histogram? There are 2 parts. After histogram equalization, what happened? The histogram will be changed like this. Changed like this, completely white side. Okay, enhanced, somewhat enhanced. But another step is there. What is the next step? What is next step? Anyone can respond? What is next step? Histogram equalization is over. What is next step? Please respond, anyone. Hello? Hello? Am I in the next step? And anyone respond, please? Am I audible or not? Yes, matching. So how we are going to matching? Here I am using A is specified. Here I am specifying. I am using this specified function. B is transformations. A is specified function histogram. B is transformation, and C is, this is my transformation. Curve 1, curve 2, and C is, what is C? What is your C? Enhanced image. So somewhat enhanced or not? Previous one is this one. And what is D? So enhanced image using mappings curve 2. So there are 2 curves, curve 1 and curve 2. Curve 1 for normal your histogram. This is the curve 1. But in second case, histogram equalization, sorry, histogram matching. So using this matching, here in this case I am showing 2 graphs, curve 1, curve 2. Okay. After matching, my image is completely enhanced or not? Here I am showing 4 figures. Figure A, figure B, figure C, figure D. So in figure C, my image is, what is my image? Is enhanced. Compare these two, previous one. So in first case, somewhat very parts are not visible. Some parts are not visible clearly. In second case, somewhat visible but very white. But in third case, that may be enhanced completely with the help of histogram matching. So after histogram matching, my histogram is changed like this. So if you compare, first histogram is like this. First histogram is 2 parts. Part 1, part 2. Part 1, part 2. Okay. In second case, what happened? Histogram equalization. Due to histogram equalization also, there is a change in histogram like this. Next. Third case, third case is histogram matching. In histogram matching also, my histogram is changed. So in my histogram is distributed as like this. So this is the application of histogram matching, right? This is the application of histogram matching, today's topic. However, histogram matching is also used for enhancement of an image. So once again I am repeating this simple concept, and don't confuse, very easy. And uh, first I have to start a histogram matching again. Unlike your histogram equalization, of course, in histogram matching we are using histogram equalization also, but in histogram equalization we are using original image histogram values only. But in our histogram matching we are using different histogram process. That means we are specifying another histogram. So our input image is transferred to another histogram, which is our specified, that can be specified by ourselves. Okay, so due to this called as histogram specification also, histogram matching or histogram specification, and that means we have generate a processed image that has a specified histogram. That means after process the image, the histogram is different than your input image histogram. Simply the difference is after processing the image, having this histogram which is specified by ourselves and which is definitely different than your input image histogram. That is our main motto here. So for that, here I want to just a minute. So for that I am using two probability density function PR of R and PZ of Z. So these two denotes two probability density functions. PR of R is our input image probability density function, but PZ of Z is our specified probability density function. Input image specified function, probability density function, PZ of Z is our specified histogram PDF. So there are two PDFs. So now we have to write the two PDFs. For first one is S equals to TR of R and L minus 1 integral 0 to R. That means S is nothing but your equalization process. But after equalization process is over, what is next? Again we have to derive the transformation function or transfer function G of Z using the same process, but which is equals to what? Your equalization process, yes. So first find out the S and G of Z, and which is equals to S. So with this we can have some process, that means inverse process. Z equals to G inverse of S. So simply it is having some three steps procedure. The procedure is find out transformation function or equalization. The first step is equalization, histogram equalization. Second step is find out the or obtain the transformation function from the specified histogram. The next one is mapping. Z equals to G inverse of S means mapping. That means S naught equals to Z naught, S1 equals to Z2, maybe or may not. Sorry for the previous one. S naught may be Z naught, S2 may be Z2. S naught nothing but S naught equals to maybe Z3, S1 equals to maybe Z4, like this. So those values are matching to the S naught. We have to map like that. Okay. Next. This is for just for continuous image. Here I am showing. Don't bother about this. No need to. Just for the examination purpose only you have to write. Just simply this is derivation for obtaining of your that means histogram matching for continuous image. Okay. Just simply substitute your PR of R here you will get S, and similarly substitute Pz of Z here, you will get your integration value, and which is mapped to S, then you will get Z value will be like this. It is very easy, just a simple integration process. But this is only for analog. The next one is we have to extend the same to the discrete values. What is the discrete value? In discrete case also there are three steps. First step is equalization process. Second step is derive the transfer function with the help of specified histogram. And the last one is simply again mapping process. Mapping, that means Z0 equals to maybe Z3, Z1, Z4, whatever it is, depends upon your derivative. Okay, na? Okay. So for this, I am taking one example. My example is having two tables. First table is for probabilities for the first histogram of a original image, and the second table is our specified histogram. Our specified histogram. That means we have to matching our histogram to this specified histogram. That is our motto. That is our requirement here. So for this, my consideration, my image is 3-bit image having 8 levels. That means R0 to R7, and the size is 64 by 64. That means total pixel values are 4096. Okay. I am starting the first procedure. First step. What is my first step? In first step, derive the all transformation function values. That means histogram equalization values. What are the histogram equalization values? These are all we have derived. S0 to S1 to S2, S3 in equalization process. The same values here I am producing 1, 3, 5. Okay. After you are obtained histogram equalized values, the second step is compute the G. What is G? Of course, G of Z0, Z1, Z2. Okay. After obtaining your G of Z, nothing but G0 to Z0 to Z7. Our requirement is draw the graphs like this, same. Okay. Here I am mapping. How we are going to map nearest values? What are the nearest values? S0 equals to 1, which is directly equal to Z3. What is the reason? Your Z3 value is 1. Okay. S1 value equals to 3, but in this there is no 3, or approximately equals to 2.45 or 2. So due to this reason, S1 is mapped to Z4. Okay. S2 is mapped to 5. The Z5. What is the reason? Your Z5 value is 4.55 and approximately equals to 5. So it is equals to or mapped to Z5. And S3 like this. S4. S4 is mapped to what? S4 is mapped to S4, S5, S6, S7. All are approximated to your 7 value. So this reason here I am mapping like this here. 3 stages: input, equalization, and specified. Input, equalized, specified. Okay. Input side 7 levels, but in equalized how many levels? Only 5. 1, 3, 5, 6, 7. These are my scaling values. These scaling values are same mapped to in transformation function. 1 to 3, okay, 3 to 4, 5 to 5, 6 to 6, 7 to 7. So that means my S0 value, that is 1, is mapped to Z3. My S3 just 1 value is mapped to Z4. Z4 value. My S2 value is mapped to Z5. My S3 value, 6 means S3 values mapped to 6. Remaining all, what are the remaining? S4, S5, S6. S4, S5, S6, S7. All are mapped to 7. So S0, S1, S2, S3, S4. S0 is mapped to Z3. S1 is mapped to Z4. S2 is mapped to Z5. S3 is mapped to Z6. S4, S5, S6, S7. All are mapped to 7. Okay. Here I am skipping middle one. Just how the directly mapped from RK to ZQ. So 0th scale mapped to 3. 1 scale mapped, first scale mapped to 4, Z4. second mapped to Z file, third mapped to 6, fourth, fifth, sixth, 7, all are mapped to 7th scale of your specified. So with this I am again showing your graphs, original, specified. Just a minute. This is original. Sorry. This is original and this is specified, and this is transformation function for your specified, and the next one is image function, that means histogram equalize matching function. So graph. So with this, and next one is there is a function application to the application is histogram matching. That is, I am taking one NASA image with some part is dark, some part is dark, some part is white. This is white and this is dark. So this is my histogram. This histogram is matched to histogram is next histogram equalization and histogram specified or histogram matched. So with this I am highlighting or enhancing the image of a dark and or low color dull colors images. So and remember this is a monochrome, not a color image. So okay, now this color image, this monochrome image can be enhanced with the help of histogram matching or specification, histogram specification or histogram matching. So we have completed with this the second application, the second concept, that is called as in histogram. Histogram equalization is over, histogram matching is over. Two topics. There are another two topics: local histogram and statistics. So we will, with this I am concluding today's topic, and in next class we have to discuss histogram, local histogram and statistics. Okay. Thank you. And already it is 10 o'clock. Thank you for everyone. And I'm leaving. So we can end up.